Hello, everyone. Good afternoon, and welcome to our senior design 1 presentation. My name is Carlos Piquera. We have Yadier Zarabozo and Fran Alonso. Our advisor is Dr. Tramante, and our project is about the use of Stirling engine to pump water on solar collectors. According to the U.S. Department of Energy, the water heater is the second most expensive appliances in our house, accounting for over 18% of our monthly electric bill. This is not only due to the use of faucets using hot water, but also many modern appliances like dishwasher and the washing machine, coffee machines, and so on. They can also use hot water as well, and they advise us to use the water in the most efficient way possible. Being a state plumbing contractor for the last 3 years, I've seen the installation of many systems to try to increase our independence from fossil fuels and use renewable sources. So the motivation of this work is to use clean energies that are renewable energies, like the sunlight, that can reduce the cost of our utility as well as minimize our power consumption in homes and business. Solar panels are very popular in the world today with the implementation of these two types, which are the most popular ones. The one on the left, the ones we're more familiar with, the photovoltaic panel, which it converts the light of the sun straight into electrical power. And the one on the right, it's called a heat collector panel, which it stores the thermal energy provided by the sun into the hot water. These solar collector panels are used in systems like the ones you see here. The one on the left called a closed-loop system. This one uses a solar collector panel, a pump, and a storage tank. It's called closed-loop system because it has a separate circuit from the drinking water, and it works a bit like a heat exchanger in the collector tank. And you also have a external source of heat, like the boiler in this case. The one on the right is called open system, which it will circulate the potable water through the panel. Also uses a circulation pump and a storage tank, as well as an external source, like in this case an electrical heating element. But both of these cases, you require a use of a circulation pump to pump this water through the panels in order to obtain the hot water. Now, this circulation pump, it's the only element in the system that uses electrical power where the system is in use, and this pump can be expensive, up to $500 to replace. And since it's the only element that uses electrical water, our goal is to find a better means to circulate the water. And we want to create a system that uses the thermal energy stored on the water to provide mechanical power in order to power a pump that we can use to circulate water through the panel instead of using electricity. And we want to create a system that it's cost-effective enough, it saves enough energy that will be liable to build, and it will save money through time.
So our solution to this problem is to replace the existing electric pump for the new Stirling engine assembly. As we know, the Stirling engine works with different in temperature in order to generate mechanical motion. This mechanical motion will be transmitted to the pump in order to recirculate water from the solar collector to the system. The Stirling engine, how does the Stirling engine work? We have 3 types of Stirling engine. We have alpha, beta, and gamma. Alpha contains 2 separate power pistons. One is hot and the other one is cold. The hot piston is situated inside the high temperature heat exchanger, and the cold piston is situated on the low temperature heat exchanger. Beta has a single power piston arranged with the same shaft as a displacer piston. The displacer piston only serves to shorten the working gas from the hot heat exchanger to the cold heat exchanger. And gamma is similar to beta, and this is the one we're going to choose because it's more efficient at a low temperature.
Okay, for the design analysis and constraints, our main worry is if the power generated by the Stirling engine is going to be enough to power the system. Also, we are still dealing in which is the best approach to transmit that mechanical motion to the water pump, either using pulleys or gears, in order to obtain the appropriate water flow that we're trying to match the 25% of the flow that electric pump produce. With that, we're gonna have to design the impeller of the pump. When designing an impeller, there are three considerations to have in mind. Some of them are the flow of the flow rate of the water, the speed of the pump, and the head change. There are three types of impeller: the open, semi-open, and enclosed. We're focusing on using the semi-open, which is the one that moves more fluids at low RPM. These are some mathematical relations that we're going to be using in order to select the appropriate impeller. As I said, the volumetric flow rate, the specific speed of the pump, which is going to allow us to select the appropriate shape of the impeller. Also, the power of the pump as well as the torque.
We had some ideas when we started to put a design together as a proposed design. The first one on the left here, it was the idea to put the Stirling engine pump assembly directly on top of the water heater. The problem with this is that it will only work with some applications because it requires a water heater to have the inlet and outlet coming from the side, as well as some insulation will have to be removed, and this can compromise the integrity and safety of the plants, of the original plant. And the other option was to design a compact pack that will have the solid collector, the pump, and the storage tank all combined together in a single unit. That was the other idea. It's good because it will minimize the amount of piping and also the head loss. But this design, it will be exposed to the elements, so corrosion will be a major factor, and it would be more costly to build.
So for our final design, we are thinking in using a separate tank connected to the main line coming from the solid collector. We're thinking of placing this Stirling engine pump assembly on top of the tank, which this system is gonna contain an electric motor in order to start the movement of the Stirling engine, and it will be disconnected by itself once the system is working smoothly. Once we have decided in our final design, we're going to be a prototype which is going to allow us to test. We're going to be using solid workflow simulation in order to compare those results with a real-life test. With that, we're going to try to achieve, as I said, at least 5 gallons per minute, which is the 25% of the electric pump.
So for the standards, we have different types of standards. We have the standard for the Florida building code, we have the standard for the Stirling engine, and we have the standard for the centrifugal pump. This system can be applied in different scenarios, like tropical, subtropical, stay around the world. It also can be applied with different pressure, and we're going to use the pipe as a different measure in SI unit or English units. So to conclude this presentation, what benefits are we getting in order to create the system? We're going to try to we're going to try to eliminate any relation with the fossil fuels. We're going to reduce the consumption of electricity of any residential or commercial business, and we're going to prevent the pollution of the environment using more clean energy.
Thank you everyone for listening to our presentation, and if you have any questions, we'll take them now.
Comments to the team?
Can you talk more about the economics about it?
We are, well, the existing electrical pump, it costs to replace around $500 off the pump itself, not counting the labor. We want to stay within that limit, be under $500. So we have looked at some parts that we want to incorporate, and I think we'll be able to achieve the $500 mark.
Just with the use of solar collectors to heat the water that uses houses, you are saving from 25 to 40% of the electricity bill. With this system, we're trying to increase that saving at least 10 to 15%, eliminating all the electric element in the system. So a year, as the United States Energy Department says, with that system, we could be saving at least $400, $500. And once the system is paid, we're not gonna have to pay for more hot water until the system breaks.
How feasible is it to have your water tank lying on its side? And considering space in a home, I mean, not anything extravagant, but let's say my laundry room, which is, what, 10 by 10? Okay. You know, how feasible is it to have your water tank lying on its side? And in terms of making sure that its operation is according to, you know, you want a water tank to work.
We are, and for this system, we're focusing on replacing the pump only, just the pump factor. This assembly, it's going to be a separate assembly from your water heater, which is going to maintain those electrical elements for backup system when you don't have hot water. And this system, it's not supposed to take more than a foot or a foot and a half on space. It can be mounted on brackets on the wall, and it can be mounted somewhere close to the water heater where you have a space. Actually, the pump itself, the recirculation pump, it's already a good 10 to 12 inches long into the assembly. So our idea was mainly replace that system with ours, and trying to make it integrable to what the systems that are already being used in all over Florida with solar collectors. So I think that spacing, because of the size of it, it's probably going to be around the same space that will take for you to install a recirculation pump, electric recirculation pump.
Any comments? That's it. Thank you very much.
Thank you.